Welcome everyone to our May edition of our First Fridays. Claudia Fritz has been studying this issue of how to um, evaluate the perceptual qualities of instruments and versus the actual construction and other attributes of the instruments for a long time. I think for over 2 decades now, at least since her postdoc at the University of Cambridge. So this is her latest findings. So welcome, Claudia.
Thank you, Fan, and good evening or good morning or good afternoon, everybody. So I will basically give two talks. So they are based on two conference presentations I did. So this one was done in December 2023 at a conference in Sydney. And then I will present some more recent work, which I presented on Wednesday at a French conference. So the first one is mainly a work with George to develop methodologies in order to better understand how sound qualities of violins are perceived. So there were many studies dedicated to find relationships between acoustical properties and sound qualities of violins, but they were mostly inconclusive. Even the recent ones with proper perceptual tests were at the end, we never really able to link the perception with the acoustical properties, mainly because players and listeners do rarely agree. In addition, it's difficult for players to decouple sound from playing qualities. And so their judgment of the sound of a violin is always mixed with what they feel under the bow, with what they are used to play. And so we believe that listeners may have more robust judgments, which could be more easily correlated with acoustical measurements, which do not take into account the player. So what I talk about more robust judgment, I'm really talking about the sound here, okay? And because the problem with acoustical measurements is that the player is not involved. It's just one measurement per instrument. And we know that an instrument will sound quite differently with different players. And so because we have only one acoustical measurement per violin, or like a series, but it's a violin always excited by a hammer, we don't measure the interaction between the player and the instrument. And so we think that maybe the listener may be more robust because they will not be sensitive to playing qualities. But the problem is like how to listen to the violins, played by whom, and which excerpt, in which venue, should it be live or via recordings? And these have been questions that we have always been, struggling with, and we have made some choice, especially for all the Strad and versus new violin studies that we did some long time ago now. So, but it's always a question. And even when we do these blind tests at the workshops, it's always a question, what do we play? And some people like Fan are really like scales. Some other people say, no, scales are too boring. And, but it's always a question. So how much of the Welsh should we cover? And then there is, of course, the problem of the reproducibility of the player. The player makes their own sound. They deliver a musical performance. And so it's maybe possible that the differences between instruments can be smoothed out. And there is evidence about this because I did studies where I investigated what listeners could reliably tell apart between, a given violinist who play different violins or play different bows. And actually, listeners were not able to tell whether a player was playing twice on the same violin or two different violins in a row. So just because the player can smooth the differences or can actually enhance differences, even if the same violin, because it will play differently. And so we were totally lost and could not tell apart. Could not say whether two violins were played. The two violins in a row were actually the same or not. So the goal of this study was to explore and answer the following questions. which one would be best for maximizing differences between instruments, capturing real features of the real violins, and maximizing the likelihood that these differences can be correlated with acoustical properties and construction parameters, and not with playing variations. So we used the 6 Bilbao violins because that's a very nice set, which is very nicely documented. I suppose all of you now know which are the 6 violins, but just in case, everything was the same as much as possible, except for controlled variation of thickness. And so we had 6 violins with a variation in either the top thickness or the back thickness. So we have 3 violins which have a medium top and thin, medium, or thick back. And we have 3 violins which have a medium back with a thick, medium, or thin top. And the middle one was built twice to see whether we were able to build twins and to basically put the differences between these violins in relation to the difference between 2 supposedly identical violins. The 3 recording methodologies were the following. We had live recordings, a real player with real violins. We had a hybrid synthesis, a real player with virtual violins, and a bowing machine, which I would call an artificial player with real violins. So the live recordings were done in a pleasant room for playing the violin. We recorded one player who played the same Glazunov excerpt. On the 6 violins, we made sure that the player was moving as little as possible, was as close as possible, at the same place as possible compared to the microphone. And we didn't have like particular instructions to the player. The idea was he would play as well as he could, something that makes sense for a player. You know, you have a violin, you try to play as well as you want. On each violin, you don't want to sound awful. For the hybrid sound synthesis, this relies on the fact that when you apply a bow on a string, that will set the string into vibration, and this vibration is then transmitted to the bridge and the body of the instrument, and that will give you the output sound. And this is called a filter. And we can actually do this filter, which is in practice a convolution. We can do it digitally by convoluting this piezo string signal, and thanks to Jim for the picture and for the piezo signals, and by actually measurements of the impulse response of a violin. So the impulse response was measured traditionally with the impact hammer hitting the corner of the bridge, a microphone at about 20 or 30 centimeters, and average all over the instrument. So this is a piezo signal. Now you understand why for the live recordings we use the Glazunov, because it's the same excerpt in both cases. And this is now the convoluted synthesized sound file. And for the last one is a bowing machine. So here we cannot play Glazunov or anything. There is no robot activating the fingers. So we just played open string. There is no force sensor, but because the violin have exactly the same geometry, it was not difficult to control the position of the automatic bow and the force applied on each string, because it was just a question of like positioning, and as the geometry being the same, the positioning was always the same. So very automatic signals, but we thought, okay, we know, I mean, so far we were always trying to maximize what we call ecologic validity, which means, you put the player or the listener in the most natural environment to make sure that you will get answers which are meaningful, so that you can extrapolate your results in a laboratory setting to the real life. But it has proven to be challenging first to actually achieve these conditions. And as a result, I'm feeling more and more that it's too complex, and we are sometimes finding difficulties to actually find correlations and answers. So here the idea was to actually go as extreme as possible to have something completely artificial and see whether we will actually get something interesting out of it or not. Okay, so we designed a listening test online. Listeners had to actually rate the 6 instruments on 2 scales. So you can see 6 bars, which were positioned randomly for each test, each player. And they could, when they would click on the bar, the green bar, they could listen to the violin, and then they could actually slide and move the bar to actually position it. So it's a ranking and a rating at the same time, because of course you rank them as they are, you order the violins, but because you actually put them on a scale, you rate them at the same time. Why these 2 broad criteria? First, loudness, because I have the feeling, based on all what we have done, that the only criterion which actually is unambiguous for people. So we all know what loud means. It doesn't mean that people agree on which violin is the loudest, but at least there is no problems of semantics. We all know what loud means, and there is not the question, what do you mean by this term or not? So we thought, okay, that's a good candidate. Timbre quality, it's kind of the same, because we don't go into the detail. So we know that it's basically the sound quality, whatever it is, whether it's rich or bright or whatever. And so it's basically kind of a preference rating, which people would prefer in terms of the sound quality. We know that loudness overrule everything. For the timbre quality, the sound files were compensated in loudness. Okay, so here we kept them, the raw recordings. Here we compensated in loudness, so we would only have differences in the timbre. So here are the results. So we had 27 participants, 15 violin makers, 6 violinists, 4 other musicians, and 2 others, average age of 45 years. So here are the results for timbre on the left, loudness on the right. We have the 6 violins. They are labeled by the numbers that Unai gave to the violins from the first test, so we all know what they refer to, but doesn't really matter for now. So the 6 violins. And then we have the ratings for each of the violin for the different conditions, so live recordings, hybrid synthesis in blue, bowing machine on the D string in green, and bowing machine on the G string in light blue. And so for each violin, we see how well the rating. So the ratings are plotted as an average over the 27 participants, which is in the middle of the bar. And the green bars here, or the red bars, or the bars actually are the 95% confidence intervals. So it's very easy to know whether it's significant, statistically significant, if the bars overlap. That means that there is no statistical difference. If the bars are not overlapping, they are spread out, then it's statistically different. So for example, here, violin 4 was definitely much less appreciated for, will be much softer for the hybrid synthesis than violin 1. And this is statistically different because this bar here doesn't overlap with this bar here. I normalize the weighting, so basically each weighting is taken against the mean because I wanted to see actually the differences. So we can see first that the evaluations of a given violin can differ quite a lot between recording methodologies. This is, for example, this violin was among the top for timbre in the live recordings and on the D string, but then was in the middle of the range for the hybrid synthesis and even lower for the G string. What else can we see? We can see that the root mean square of the differences between the violins. So if we look at how different the violins were judged, we can see, so basically we can look at the spread against the zero mean. So the further you have violins like this, the further means the more people would differentiate between the violins. The closer all the ratings are to the central line means that people would just put all the violins together. You know, for example, they would rate them 4.55, 5.5, 6, you know. But if you have big differences, then people would put them, for example, they would put one at almost 0 and another one at almost 10. What we can see is that this difference is higher for the bowing machine, for the G string, a bit lower for the D string, even lower for the hybrid synthesis, and very low for the live recordings, with a difference of almost like half. So that means that people had heard more differences on the bowing machine, on the G string, than they heard on the live recordings, which goes well with our previous observation that the player will actually smooth differences, and so the violins will appear to be closer to each other than they would on a bowing machine, which can't adapt to the violin. So, but then we feel, okay, so the bowing machine based on this would be the ideal candidate because it will actually emphasize the differences. The only problem is, like, of course, you have to separate the different strings. You don't have the full range of the instrument, so it's still a bit problematic. And people hate listening to a bowing machine. And so how is that really the most relevant way of testing? So we did another study where this one, we really wanted people to match the real violins with the recordings. So 6 violins were a bit too much, so we chose 4 of them. And so basically they had the real violins at hand and they would have 4 recordings, either for live recordings or for hybrid synthesized stimuli or for bowing machines, recordings recorded with the bowing machine. We had a listening session with a violinist who played the violin for everybody, because we know that some violin makers don't play much. So we had first a listening test. People could take notes about all the violins, and they could use their notes during the test. And then during the test, they were allowed to play the violins as they wished and compare. And so basically they would have to say, okay, violin 4, where it is? Is that this recording or this recording, and so on. So here are the results. Did I say, so there were 13 participants which were, who were violin makers and violinists. So the results, so for the hybrid synthesis, there were 30 correct answers out of 52 and 6 participants out of the 13. So just less than the half had a perfect match. So that means that they recognized all 4 instruments. So that's far beyond chance. For the bowing machine, slightly less correct answers, 26. And actually, but even half of the first number participants had a perfect match. And then for the live recordings, that really drops with only 12 correct answers out of 52. And at most, participants had 2 good answers out of the 4. And that's at most for only 4 participants out of 13. So for everybody else, it was just like completely random. So based on this, we feel like the hybrid synthesis actually capture best the differences. So maybe not in an absolute way, but at least in a relative way, they capture best the differences between instruments because people found it easier to actually match with the real violins than they did with the live recordings. So based on both parts of the test, we can see that live recordings do seem indeed to smooth out differences and introduce variabilities, which are then not felt by listeners when they look at the violins. The bowing machine is very artificial and very tedious and doesn't provide enough information to match with real recordings. So the hybrid synthesis appears as the best option. But that, of course, this was the conclusion for my talk at the conference, is still, even if we know now which violin is best or better liked in terms of loudness or better preferred in terms of timbre, we still need some more work to make the correlation with the construction parameters of the different violins. I can just comment on this. The V4 is the thick top. So that's quite consistent, is the thick top. Sorry. Could you not play? Eric, est-ce que tu peux aller plus loin parce que ça s'entend là dans la... Je suis en conférence. Merci. Sorry, some people are talking upstairs and it's resonating a lot. So what we can see is that the thick top is definitely has a definite lower sound quality and it's softer. And this is something that we have seen in all the tests we have done on the Bilbao violins, all the different listening tests in Bilbao, in Oberlin, the players. There is one consensus, which is this one, that the top, the thick top is not liked in terms of timbre and loudness. But for the other violins, there is nothing very clear, and which has already been. So to actually correlate this, and especially that there is big variability in the perceptual evaluation, is not very easy to actually correlate with the construction or the thickness of the plates. So the study was published 2 days ago, finally. And so included were Unai, because he did an amazing job on the Bilbao violin, and so all the study was done on the Bilbao violins. And Jim Woodhouse, who helped me at the end for the revision after George's passing. I have to say that the paper was accepted, but had to do some minor revisions. I did all the revisions. Then it got kind of sent back, saying that the revision should be major now. Then George died. I had no energy to go back to it, and Jim kindly offered to help me with this, with the revision. And so it's available. It's open access, so you can easily find it if you are interested to know a bit, to have more details about the study. So I don't know, maybe we should, yeah, I should take questions now, and then I could do the next talk, but I think it's probably better to have questions.
Okay.
Yes,
So,
Joseph?
Well, thank you, Claudia. That's congratulations on the paper. And that's a very positive finding to me, because the synthesis is something we can do easily. I was confused. I think we've had a thread about this earlier. You said you measured the sound from various positions. What did you use? I mean, were you using the complex average or the monopole radiation?
Yeah, so in the end, I use the complex average because I need the phase to do the convolution.
So it's even more astonishing that you can recognize the violins without a lot of the high frequencies.
Yes. But actually, I think, I mean, the thing is, like, the complex average will cut out the higher frequency, but it will probably cut the same way for all violins. So I think relatively, it's okay. The funny thing is, like, on this with this hybrid synthesis, I actually tried to better understand how people would recognize the violins, and so I did some very dramatic cuts. So I cut all the sound files above 1000 hertz, and people like George could still recognize the 6 violins. And then I did the opposite. I cut all the frequencies below 1000 hertz, and people could still recognize the violins. So that means that there is information which is relevant in basically everywhere. And when you judge relatively, as soon as you have some relative information about the violins, you still recognize them. So more investigation would be needed too, because I did like dramatic things, everything above, everything below. But I was astonished that by being so dramatic, people still could recognize in both cases. That was quite amazing.
So if I understand you right, they could recognize in both cases at what percentage? I mean, how often were they right?
So it was far above chance. Some of them, like George, they did all 6. They found all 6.
Because with the complex average, you're hearing more the signature modes and comparing those, and that's interesting. Well, I don't know. Without the highs, you're not going to get a lot of loudness differences, it would seem to me. But so in principle, you could do the study again using individual microphone positions, but of course,
exactly,
whether it's worth it or not, but that would also tell us something.
Yeah.
Well, very good.
Yeah, so there are plenty of routes to go further, like taking only one microphone position, applying some filter to kind of cut some information, and do we still recognize the violins or not? Where is the relevant information, or at least to differentiate the violins, or so there are plenty of. I will talk a bit about it in the second talk.
And did you try giving a player listen to the synthesis and then trying to recognize the violin by playing it? Does that work?
Well, that's what they did here.
Ah, okay. So it wasn't listener, it was a
No,
player.
yeah. The certain participants were able to play. So some of them didn't play much because they are not good players. So they just bowed the open strings, or they would test like a violin maker would do. Some of the participants were violinists, so they would play them more thoroughly. But they could play whatever they wanted. But for the recordings, that was only what I demonstrated before. So just the Glazunov or the G for the bowing machine.
Oh, that's a real finding then. That's great.
Any other questions? Wow, no questions, at least for now. All right, Claudia,
does it mean that it's very clear, or does it mean that people are sleeping?
All right, let's go on to your next section, and I'm sure there'll be more questions and discussions at the end.
It says that my connection is unstable. Did you have a problem with
Not yet.
hearing me, or okay?
You're occasionally having brief freezes, but it always comes back.
Okay, I've just changed the router, so it should be better now. Okay. So this is basically the results are from last week. So it's like a very recent study. So it's to investigate the violin model on the sound, in particular Strat versus Del Gesù. So it's a study with my interns, Angelica and Clémence. So Clémence was last year, Angelica is right now at the lab, and MJ and Sam. So I think here I can skip the context because this was for scientists. So I don't think you need this. I was explaining that violin makers would easily spot which one is a Del Gesù, which one is a Strad based on visual cues. Scientists couldn't believe it because they could barely see any difference. They say, what? Is it different? But yes, Del Gesù on the left, Strad on the right. But what is so, I mean, with training, it's obvious that people can do it and there is nothing surprising. What is more surprising is that it is believed that there are characteristics which are specific to Del Gesù instruments compared to Stradivarius instruments. And I just have a quote from Bain and Fushi. Guarnero Del Gesù violins tend to exhibit a deeper, darker tone than the silky, rich tone of a Strad. Players who prefer a shorter scale length, a darker sound, and a limitless cache of tonal variants tend to prefer Guarneri. Players who prefer precision and refinement tend to prefer a Stradivari. And so, but so the question is like, the problem is there is no a single Del Gesù model, there is not a single Stradivarius model. So yes, the model can make a difference, but how would it be in average? And, you know, we know as well that the wood which is used and the varnish and how you assemble will make a difference. So is there any reason to believe that the model will have a stronger influence? Some people have already investigated this question, especially in terms of spectral differences. So there is a study from Anders Buen, who computed the average spectra on commercial recordings of a soloist on 15 Strad and 15 Del Gesus. There were, so the soloist was Elmar Oliveira. And so there was one solo excerpt of 1 minute, which was actually played on the 30 instruments. And then there were the set was divided in 15 pairs, Stradivarius and Del Gesù, and each pair was played with a different excerpt. 7 were actually solo and 8 with piano. And so Anders did some long-term average spectra divided by in bands. He showed some differences, but it's not very clear whether they are statistically significant. And there is no link to perception anyway, not systematically at least. Then there is a very recent study of Sebastian Gonzalez, who have worked with MJ and Sam on a collection of violins from Sam's production. It's not published, it's just a preprint on ResearchGate. And they show that the average reducibility profiles between the two families can differ by a few dB in certain bands, but they didn't find any significant differences in terms of modal parameters linked to the first 4 modes. That is what that was in the paper, frequency, amplitude, and Q factor. And then there was a study I conducted with Joseph about testing this in a perceptual study. So we organized a blind playing categorization test in which there were 9 violins, 5 Strad models with actually 2 authentic Strads, 3 Del Gesù model with 1 authentic Del Gesù and 1 other completely different model. We had 21 participants who were good violinists and maybe a few violin makers who attended one of the VSA convention. And so the results can be shown as what we call a hierarchical tree. So how do you look at this? Basically, here on the vertical axis, it shows the differences between the violins. So the smaller the length is, that means the closest the violins were. In another way, that means as well that more people put them together. So these 2 violins here, 2 and 6, were definitely put much more together than 2 and 6 and 8 and 9. So it goes this way. So basically we can see, if we start from here, we can see 2 subgroups, and each subgroup is divided in 2 other subgroups containing 2 instruments, 2 instruments, 2 instruments here, and 3 instruments here. What we can see is that here, actually, the Del Gesù models were grouped together, but these 2, 3, and 7, they are strads, and you can see that they are not separated from the del Gesù. They could have been put together with the strad, and then we would have a clear separation with the del Gesù on one side and the strads. But we can see that the 2 strads were put closer to the del Gesù than they were to the strads. So there is something, but not clear. One limitation is that we don't have the same number of del Gesù, and so we are missing a bit some del Gesù models. But we did with what we could have at the time. And then we looked at the verbal description provided by the players. So I forgot to mention, this playing categorization test is basically based on cognitive psychology, saying that we are used or trained from our early age to do classification. You all know that what you call a table is because it's something flat with 3 or 4 feet. You know, we know that the mammals have 4 legs and they are different from the spiders, which have 8 legs. So we are used to classify. So this is a very common task to do. And the procedure rely on the fact that you actually don't specify anything. You just ask the players to categorize by similarity. And what similarity means is left open. Okay, so some players may actually say, okay, I put this together because I like them, and I put these other 3 together because they are very soloistic, and these 2 because they are dark. They can have different criteria for different groups. They have their own criteria. So it's quite powerful as well because it doesn't put any a priori from the experimenter, because that's always the problem is like as an experimenter, if you ask the question a certain way, you will have the answer which goes with that question. And if you had asked it differently, you would have had another question. So here is the idea that you have a limited influence of the experimenter and the a priori of the experimenter on the outcome. And so the people were free to make as many groups as they wanted. And they had, at the end, they had to describe each group that they made. And so we looked at their verbal descriptions to see as well whether we could actually see something in their verbal description. And actually, we had some players saying that the Gesù model were the bassiest, darker, warmer, and darker sound. But at the same time, we had other players who actually said that they were the bright group, or they were in the bright group. So people definitely didn't agree on something as what we could almost call objective as brightness, which was quite surprising, and it doesn't show anything related to what people claim with del Gesù being bassist and Stradivari being a bit brighter. But as I said, not many del Gesù models, and so we thought, okay, let's take advantage of all the collection of data made by Sam and MJ on the Sam's production. So they have collected since 2018 a full data set of radioactivity and construction measurements on 22 strad models and 38 del Gesù models. And Sam and MJ are really convinced to hear systematic differences, and they have actually formulated hypotheses based on the radiated amplitude in certain frequency bands. So the goal of this study here is to test their hypothesis thanks to acoustical analysis in one way, and perceptual studies, so actually listening tests based on the hybrid synthesis, because as the previous study showed that it's a good way to do it, let's try it here. So here, I mean, I can make you listen to the piezo recordings once more. And here one of the synthesized sound. And because Jim gave me a few recordings, we don't have always the Glazunov, but we have Tchaikovsky and Sibelius as well. I put this picture because it's what I had, but MJ and Sam are not using an anechoic chamber, of course, and so they are doing it in the workshop, trying to be as systematic as possible.
Can I just ask Claudia, what microphone position were they using? Or did you use?
It's 20 centimeters.
from the front center?
Yes.
Okay.
So here are the average radioactivity profiles. So in red, we have the strads. So the solid line is the mean across the 22 strads. The blue solid line is the mean across the 38 Del Gesù. And then you have shaded areas which represent the confidence intervals. So as I told you, when the confidence intervals overlap, that means that there is no statistically significant differences. When they don't overlap, we can expect some statistical differences. And we obviously have areas where they do not overlap, like here and here, but there are plenty of places where they do overlap. Now, statistically significant doesn't mean perceptually different, you know. So here it's just looking at the spectra, and now we want to investigate whether we actually can hear the differences. So MJ and Sam have like a very strong hypothesis in 3 bands: the lower transition hill, where they say that because the strads are a bit lower than the Jesus, that should make a difference. The higher transition hill, where strads are much lower here than the Del Gesù. And then the lower bridge hill, where actually the strads are higher than Del Gesù. And they believe that they actually can hear this area and tell them apart based on these bands. So we first did a free categorization listing test to kind of reproduce the playing categorization test. Obviously, we cannot do it with the 22 strads and the 38 Del Jesus because it would be insane for the participants. So we selected only 5 strads and 5 Del Gesù. Here it's done online, so you have all the stimuli as little icons. You can click on them and you can actually drag and move them around to make classes. One violin was actually repeated to make sure, to test whether people are robust, and would put the repetition together with other violin. And we use something which is called TCL LabX to actually do the test. We had 18 participants, all violin makers. And here are the results. So now you know how to read such a graph. So the first thing we can see is that the repeated stimuli are put together. So yes, people can do it properly, and they recognize that 2 violins were the same, which is reassuring because that means that they actually didn't just do it randomly. But then what we can see is that we have a group here with a strad and a Del Gesù. Here we have 2 Del Gesus. Here we have 2 strads. And here we have Del Gesù and strad and Del Gesù. So we don't see any obvious groupings based on the family. You know, we don't see all the strads on one side, all the Del Gesù on one side. We see even less consistency in terms of family as what we had observed with playing test. So of course, Sam and MJ were very disappointed, and as I said, okay, they actually didn't group Strad and Del Gesù together either, you know. So, but I thought, okay, but maybe there could be some consistent differences, but which is lost because it's more subtle than actually the main differences on which you will base your similarity judgments. We know that the quality of a violin is multidimensional. And so maybe when you judge on some similarities, maybe some violins you will judge, oh, they are very similar on the G string, but then some others, but at the same time, one violin you put with another one because of the G string response, but you are like tempted to put it on with another one because of the I string response. So it's all a question of like trade-off and how you make the groups. And so it still doesn't necessarily mean. So it means that overall, there is not a clear, very obvious difference, which would people put put the violins in 2 different categories. But that doesn't mean that there is not something there which is just less subtle and which doesn't show up here. So we did a more simple test, just pairwise comparisons. So basically, we sent to Sam and MJ 4 pairs, actually times 2, because there were 2 excerpts, so 8 pairs, which were all constituted by a Strad and a Del Gesù. And we asked them which one is a Strad. So very easy, two violins in a row, which one is a Strad. And they actually did 100% correct for the 8 pairs. So it's far above chance. And MJ was so surprised because she agreed that it was kind of subtle and she was not so, she heard the differences, but she was not fully confident. So she redid the test with other conditions. So she's used it loudspeakers this time instead of headphones. She did another order and she got 100% correct again. So there is something obviously there and which needs to be understood. So I've decided to look at what we call excitation patterns. So let me explain what it means. When we look at spectra, the problem with spectra is just signal processing, okay? It's not related at all to how we perceive and how we hear. Here, excitation patterns actually correspond to the peripheral neurosensory representation of the sound signal, and they are based on how the basilar membrane inside the ear is excited. So it takes into account that we are less sensitive at lower frequencies and higher frequency. It takes into account that some masking can occur and some non-linearities can be implied. So there are loudness models that are available, and so I've processed the synthesized recordings through the loudness models. And you get these plots. And so I actually compare for 3 of the pairs that MJ and Sam listened to. I compare the excitation pattern for the Del Gesù in blue and the Strad in red. And we have the Sibelius excerpt on the top, the Tchaikovsky excerpt on the bottom. And so this is, compared to the radiativity profile, this actually takes into account that the violin was played with an excerpt, Sibelius or Tchaikovsky, and that the recordings was processed by our ear. So what we can see is that for some pairs, we have consistent differences between the Sibelius excerpt and the Tchaikovsky excerpt. For example, here, the Del Gesù is always on top of the Strad. But we have some pairs for which you actually have some inversion. Here, the Del Gesù is on top for Sibelius. But for Tchaikovsky, you have something much more mixed. Nevertheless, Sam and MJ were still able to spot the Del Gesù here. So that's why there's a question, how do they do it? We can look a bit more into details about the hypothesis that MJ and Sam have done. So they said that, and based on the radiativity profiles, we have seen that in the lower transition hill, the Strad are supposed to be lower than the Del Gesù in terms of radiativity. What do we observe here? Well, actually, yes, most of the time, but not all the time. For Tchaikovsky, for example, we don't have the Strads lower than the Del Gesù in that band. Next band is a higher transition hill, where the Strads are supposed to be much lower than Del Gesù. And here, what we can see is that it's rarely the case. It actually only happens for one pair. Okay, so what we saw on the radiativity in average doesn't translate into what we see here for the ears. For the lower bridge hill, where the radiativity showed that the Strads were higher than Del Gesù, what we see here is that it's the case by a small amount and only at the beginning of the band, so more between 1800 and 2000, where we see the red curve being above by 1 or 2 dBs, but in a constant way. And then, but what we can see that we didn't see in the radiativity profiles at all is that in the B1 plus area, the Del Gesù are always superior, or superior in terms of amplitude to the Strads. And this didn't show up at all in the radiativity profiles. So what we can see is that the excitation patterns are not in agreement with Sam and MJ's hypothesis on radioactivity profiles, and not just their hypothesis, but as well what we can actually observe on the radioactivity profiles. But though the observed significant differences do lead to systematic recognition because they were able to tell them apart systematically. Because they can do it, but it didn't show up in the categorization task, the differences might be small compared to other differences. So when you have like more freedom to choose and you have to base on a similarity, they don't lead to systematic classification. Now, that's just the beginning, basically. So now we need to do so many things to understand, what is on what is based this recognition. So we need to test more pairs, and my idea as well is to actually tweak the radioactivity to compensate for some of its aspects. So for example, instead of using the radioactivity of this del Gesù, I could use radioactivity divided by the blue line, multiplied by the red line, and convolute. So I could make like a del Gesù, which would have this like kind of a morphing between the del Gesù and the strad. And we could do it by step of different dBs. And so we could try to see at which step MJ and Sam don't recognize the del Gesù anymore. Or, so if you go from the least, the strad to the del Gesù, can you have different steps where the strad becomes more and more del Gesù, and when does it stop to sound like a strad? We can do it overall, but we can do this as well by like separating different bands to really investigate which band, or is it a ratio between bands, and how it's responsible for the differences that they consistently hear. And so that would be quite a powerful way to better understand how we listen to violins, and eventually go back to the radioactivity and give insight in what we should look at in the radioactivity profiles. And then we could do the link with the construction parameters thanks to the parametric finite element model that is presently developed by two of my students, where we could actually change in this finite element model the outline, so the model, and see how it changes the vibratory response and how we can link it to the radioactivity changes that we can measure. And that's the end for now.
Thank you, Claudia. That was very, very interesting. So questions. If you can use the raise hands function. Joseph, you're muted.
Thank you. So did you have a graph where you simply impose the average radioactivity of the strads with the del Gesus?
Yes. Yeah.
Okay, so if we visually average the red ones, that'll be the strads, and the blue ones, the del Gesu, is that right?
Yeah, the solid line is the average. The blue solid line is the average over 38 del Gesu, and the red line is the average over 22 strads. When I say strads and del Gesu, it's the models, because they are all made by Sam.
Sure. Okay, so I did a study. It wasn't published. I think probably we've talked about it, looking at comparing just the average radioactivity, horizontal and vertical, 12 positions around in each case, of 7 del Gesus and 14 strads. And it showed that the del Gesus put out more in the signature mode regions and in the upper hilt region, so above about 4 kilohertz. So the Strads are more in the bridge hill, which we're seeing there, but we're not seeing the other two things. But then I did the same thing with, I think, about 40 new instruments, some Strads, some Deljays, and I saw pretty much exactly the same pattern. And I think that rhymed with something that Martin did earlier. I think I saw, is Martin here? Did you find something similar? Maybe he's not.
He's still listed as a participant, but
Okay. So with the single microphone position in the front, it's kind of a low point for the bridge hill, the 2K. So I would be surprised if that's a very sensitive way of finding that area. The bridge hill tends to jump up if you go about 15, 30 degrees in either direction, especially.
So this is based on 4 positions. So central, 30 degrees left, 30 degrees right, and the rear position.
Okay, that's going to give a better.
But it's only horizontal tap.
Well, the horizontal should do fine with the bridge hill in the lower range. It's not going to do much with the 3 to 7 kilohertz range. Okay, I'm just trying to understand better, but so that doesn't show okay, how would you describe the difference that you see? Lower transition hill, higher bridge hill for the Strads.
Yeah.
And what's remarkable.
And then, I mean, here we do see a bit of differences, but they are overlapping quite a lot. So at least they're not statistically significant, but it doesn't mean that for a special pair that we use, if we choose by chance one Strad which is far high and one Deljezu which is low, that doesn't mean that it matters, because
Right.
we have to say that we never listen to the average. We always listen to examples, and some examples can be high and some examples can be low. So
Yes, and what's interesting about this is that when I looked at all the Strads and Deljezus, new and old copies and originals, there's a wide variation in B1 frequencies, and there's an incredible overlap.
yeah.
So in a sense, it's good. It's if we imagined, I mean, we kind of take that range of variations out, and that helps illustrate something. I don't think it's necessarily the difference between Strads and Deljezus, but anyway, Jim had a question.
But I think I remember you telling me that you had the feeling that the Deljezu were lower in frequency for the B1 mode, but we don't see it here.
We don't, because those are Sam's
Copies.
instruments.
Okay.
I think, but the confounding factor is that regraduations. Guarneri made his instruments thick, or so they say. They're often regraduated very thin. The very thick ones, like the Vieuxtemps, have extremely high B1 modes. So it's really completely different question. Are you recognizing B1 frequency and its attendant effects on upper frequencies? But so this is interesting in that it gets rid of that.
Yeah, I mean, and then I should specify that when they talk about they can recognize, when I say they recognize the Strad versus the Deljezu, they recognize the Strad model used by Sam, or some of the Strad model used by Sam, and some of the Deljezu model used by Sam. It's not, I would not claim that this could extrapolate to authentic Strads and Deljezu, because there are probably things that Sam makes more consistently between the two models than it would do in a real authentic old Strads and Deljezus.
And could other people recognize the difference? I mean, Sam and MJ were evidently very good. Could they be familiar with that set of instruments? I mean, did you try it on other people?
I mean, they're obviously, so for now I haven't, because I thought, okay, if they claim that they can, but they never took the test. So I thought, let's first check that they can, because if they can't, that's the end of the story. You know, no point of trying to find something that nobody can hear. But they actually could. And so that means, and MJ explains very specifically how she does it, and she really feels that she can hear this mid-range, and she has the feeling that the strads are lower here and higher there, and the Jesus are opposite way she could describe it, and she obviously can do it. So
well, then
yes,
if I send some IRs of Strats and Del Jesus not by Sam, would she be willing to have a go at it? That would be a nice.
Yeah, that would be excellent. Let's try this. Yeah.
Okay, let me know if I can try and round.
Yeah, yes. No, I'm sure she will. MJ is
Mhm.
always ready to take some more tests. It takes
Great.
time, but she was so happy to see that she could do it. But
I believe it. Thank
but
you.
yeah, but I mean, I think there are different questions here. I mean, first, if we understand how they do it, you know, especially that this is in average, but when we do have separate instruments, in particular, as I showed you, I was surprised that, you know, even with pairs like, I've lost my mouse, like here, where it's much more confused than here, they can still do it. So, you know, where is the perceptual information, perceptually relevant information, you know? So I think there are still, beyond the Strad and the Jesu question, I think there is a lot to learn about how we perceive violins. And then, yes, we can, as a separate question, we can as well try to better understand how the Jesu and Strads. But here I take it more as like as a challenge to better understand. And I feel like if we better understand here, then we can eventually go back to the radiativity profiles and maybe come up with a function that we could apply to the radiativity profile, so they are more perceptually relevant to what we can actually hear when we hear excerpts, not just when, yeah.
Agreed. Jim?
Yeah, this is just a small question. I mean, these are very interesting results, and it's now you've established that Sam and MJ can do something reliably. Just a thought of another way you could frame a similar question about how they're doing it. If you could provide them with some kind of graphic equalizer, then you could set them the challenge of starting with the Del Jesu sound. Can they arrange the sliders so that it sounds to them like a Strad? That's a slightly different way than you providing samples and seeing what they've done. It just set MJ a challenge.
Yeah, we discussed about it. MJ apparently had an equalizer when she was younger, and she said that she did all her training using it, playing with the equalizer and trying to hear. And so we discussed about it, and so it's definitely one way of doing it. So I have to find which equalizer to use easily, and you know how.
Yeah, I mean, so it sounds as if you ask MJ to change the sliders so that she can turn a Strad into a Del Jesu and a Del Jesu into a Strad, and then you make some pairs from those processed ones and try them on Sam, and see if he agrees with her that they've swapped which way round they are. That would amuse them, and it's important to keep your participants happy, isn't it? So
yeah, but I thought that doing the equalizing thing is as well more work for MJ, and she's already very happy to spend quite a lot of time. So I don't want to push too much either, you know. So it's a kind of a trade-off. But if she agrees, we can do both ways. Actually, one is not exclusive of the other way. So
absolutely, it's just. It would feel different from her point of view, because playing with equalizers is something she can do in odd moments until she finds the perfect thing, rather than sitting down to do a 30-minute test with an official 5-minute gap in it, and all of those. All of those.
Well, especially she has already some clear ideas of how she would do the slider. So
so exactly, she can try her ideas and see if it works for Sam. Yeah,
I don't know. She's traveling tonight, so I don't think she's here. Is she?
Yeah, I don't think she's on. Yeah.
She's on?
No, I don't know. I don't see her.
No.
Yeah.
Yeah,
So,
she said that unfortunately she's traveling tonight, and so
Yeah.
or
Mhm.
today, and she probably couldn't join.
Yeah.
Same for Sam.
Jimin.
Hello, can you hear me?
Yep.
Yes.
Hi, Claudia.
Hi.
Hey. So my question is going back to the first paper that you showed us. I just couldn't find the right button fast enough to ask a question. I was wondering about the loudness test.
Yeah.
How far was the microphone, like whatever that like you were measuring the loudness was from the instrument, and were
For the live recordings, you mean?
Ooh, I don't know. I think for any there
Because
was one.
So for the hybrid synthesis, the microphone is about 20 centimeters from the central point of the instrument. For the live recordings, I don't remember exactly, but basically the idea was what was really important to us is that it sounded good. And then we kept it the same for all the instruments. And so basically we adjusted so we had enough direct sound and a bit of reverberation. So this was more like based on aesthetical judgment, because we wanted to have extreme. So the Boeing machine was like dreadful, and this one was supposed to sound nice as a.
And
so
that's the same distance that you measured the loudness from as well?
No, I didn't measure the loudness. The loudness were just evaluated by the listeners.
Oh, okay. And how far were the listeners sitting then? Or
With headphones.
Loudness.
They were. It's based on recordings, so they were using headphones. It's recordings. They listen to either the recordings, the live recordings, or to the hybrid synthesis recordings, or to the Boeing machine. So they listen. So for each condition, each test, of course, the 6 violins are recorded in the same condition. So they didn't have to judge, one violin with a live recording and one violin with a hybrid synthesis. So when they had to judge the 6 violin, it was for one reproduction technique. And then they would do the next test, which was another reproduction technique. But it's all on via headphones or loudspeakers. I don't know what people did at home,
I see. So would it be reasonable to say that the loudness test was done with the microphone pretty close to the instruments?
No, not for the live recordings.
How far was for the live recordings? How far was the microphone?
It's probably a meter or something like this.
1 meter away?
Probably something like this. It was really like we kept it constant. For us, what was really important was not the exact distance, but more how it sounded. We wanted to sound nice, so we put it kind of above the violin. What was then important is that it was the same distance for all the violins, but the distance itself doesn't really matter because it depends so much on the room and
I see. Okay. Yeah, thank you. I was just curious if there are any like a data or research is done on how loud the instrument is perceived close to the instrument versus farther out, let's say like a 50, 100.
I mean, we have done this study with Joseph. We wrote the paper. We actually wrote 2 papers. They were not accepted. There was a lot of revision. We have started doing the revisions, and we never sent it back but it's on my to-do list to go back to these papers and try to have them published, because that answers this question where actually what we noticed. So we had people listening on stage. They were listeners on stage, so very close to the player, and there were listeners in the audience, and the correlation was very, very high, 0.94, between what people heard on stage and what people heard in the audience. So this idea of a violin that sounds quiet under the ear but projects well, we very doubtful about it because we haven't seen any evidence for this.
That's interesting because in my experience as a luthier, has been it's been quite common. So I'm just really curious about trying to find any kind of scientific studies on why that is.
What has been
Yeah, no,
common?
all the instruments that were, or maybe Joseph, you want to comment on this?
No, what has been common to you as a luthier?
There are a lot of instruments that sound very loud under the ear, don't project as much in the hallway, not hallway, in the hall, where the audiences can't really hear it as well in their ear.
How do you judge this? Is that your perception? You were very close and then you went to the hall?
Yes,
yourself?
yeah. So yeah, so when we're like, let's say like myself and some other musicians, we're adjusting an instrument in my place, which is very small, and we're trying to adjust it and in terms of the volume, they will hear it really loud under the ear and standing right next to the player. But when we go to a larger hall, that's not the case, and vice versa with instruments we didn't think was so loud under the ears, but will project pretty far. So I'm just really curious how what the correlation is.
Could I add something there?
Yeah, sure.
The correlation that was very high was between listeners a couple of meters away on stage and people further out in the hall. So it was loudness up close versus projection in the hall. And then we did another one randomly judging projection and loudness, different people, and that was very closely aligned. So we can say that projection is the same as loudness perceived in the hall, and that correlates with projection close to the loudness close to the instrument. What was interesting, and correct me if I'm wrong, Claudia, judgment of loudness under the ear didn't have nearly as good a correlation. It was still significant. And indeed, one of the best players there had an inversion, right? Remember, I think it was Nathan, other violin, the others called loudest under the ear, he called least loud. It was just the personal experiences introduces some very different variations that don't have to do with
the main problem with correlating with what the players perceive is that we have 20, 40, 50 listeners, but only one or two players. And so when we can see statistically significant effect on the listeners, we cannot see it on the players because you have only one or two players. So that's one of the, and so maybe, yes, one player made an inversion, but maybe it would have been the only one out of 10 players. So we can't really know. But definitely for listeners close to the player and listeners out in the hall, like 10th row beyond, was very, very highly correlation.
I certainly had, as a maker, I thought that was a real effect, that there were quiet instruments under the ear, that projection, I'd convinced myself. And so about the time between when I was did a project studying the Vieuxtemps and Claudia and I did these studies, I was really actively looking out for a quiet instrument that projected well. And then our tests, we never found one. I mean, there weren't any that players judged as quiet and that projected well. So
how about instruments that sound very loud under ear but doesn't project well? Have you found that?
no.
No.
Mm-hmm.
No, the very loud under the ear always are very loud in the hall.
Yeah.
Mm.
But and yet there's enough variation, I mean, an experience that there's probably more to be teased out of that. And in fact, just having different players, judgment of loudness under the ear would be an interesting thing. And maybe there's enough variations that it could allow for that. I think as soon as you get away from the ear, it becomes very reliable. That's my impression. But Claudia, I'm excited to hear that you're interested in working on that. Again, just that element, loudness and projection, I think is a very important finding. And I've been just kind of frustrated that we never got it out there. So
I
please.
know.
And most of the reviewers' objections had nothing to do with that.
Yeah, indeed.
I would really be interested in seeing that. I think it's important for a lot of musicians. And in my experience, it's been very common that something that sounds very loud under ear, it's not projecting in the hall. And we have, like myself and a bunch of musicians, we would be sitting in the hall and just being very puzzled, like we can't hear it. That's really strange. So I do think it's something that does happen. So thank you so much, Claudia and Joe.
Yeah, so just to finish, continue on the topic, because there's a question in the chat that somebody asked, how is projection measures? Can you review, you know, the study that, you know, we did and how we
So
measured
the
projection?
project was actually, it's not measured. I mean, it's measured by people. So it's evaluated by people. So people had a score sheet, and it was by pairs, and they had to judge which one was the loudest or the most projecting one. So because people say, oh, but it's different projection in the hall compared to loudness. So we actually asked the audience on stage to judge the loudness, and we asked the audience at the back of the hall to judge projection. And basically for each pair, they had to rate which one was the most projecting or the loudest. And then the correlation between the two types of evaluations, the listeners at the back of the hall and the listeners on stage, correlated very highly. To the point that I would have never expected. I mean, 0.94, you always dream of such a high correlation. I've never seen any other correlation like this. So,
And I think
So-
we made the point that loudness has a negative connotation in English. You don't want to be told, you know, your shirt is loud or your friend is loud or your violin is loud, but projection doesn't. So I think there's some evasiveness by calling it projection, which is not defined. Loudness is reasonably well defined. Projection isn't. So I think a major contribution would be just removing it and say we can just talk about loudness, period, and drop projection or define projection as loudness.
Okay. Evan?
Yeah, I want to weigh in here a little bit. So one of the things you're fighting with the description here of being under the player's ear is that's a very finicky part of the acoustic response. It's what we call a hydrodynamic near field. And so you can put a sensor in those close positions and get very large changes in level in that very narrow field. And when you get about a meter away or so, then you're having high correlation with that distance and the rest of the hall. Measurements in the very near field will very oftentimes have very localized nulls and peaks. So it's got a very irreproducible near field. And so that can be coming into play here where you get away from the instrument a little bit, everything kind of makes sense. When you get in very close, you've got a very sensitive to position, and your ear is part of that positioning going on. The other thing is you've got bone conduction coming through the jaw, which will be perceived by the player, which has nothing to do with what's being radiated by the instrument. So you've got a couple of complicating factors in that measurement, even if we make it with a microphone and not the player's ear.
And Evan, how much does bone conduction contribute to perception?
Good question. I don't know.
Oh, okay.
oh, yeah,
Yeah.
it's not clear. Yeah.
It's just you're getting different information in that playing position than you're getting in the rest of the hall. And even, you know, when you put a recording microphone out and, you know, and Claudia's, you know, meter to 2 meters away is pretty much what the audio engineering community would say. And part of that's, you know, how reverberant the hall is. So you do get, you know, get a meter away from the instrument, you're going to start seeing some stability in the radiation measurements. Get in closer, and it's like you got a little tone probe. So if you were taking the microphone and putting it real close to the instrument and moving it around the instrument, you'll see quite a bit of variation.
Yeah, sure.
You just
And definitely the audience on stage where, you know, they couldn't be 20 centimeters away from the player. So they were definitely a meter or two away from.
And if you get them about a meter to 2 meters away, you would expect them to be perceiving the same types of things will be in the rest of the hall. So
Yeah.
you'd expect to have pretty good correlation between those two measurement points.
Which means, I mean, if we could, if we could say that don't judge under your ear completely. I mean, you have to enjoy playing it under your ear, but if someone standing a few meters away thinks one of them's louder than another, that's going to be pretty reliable in the whole. Or is it the case that if it's a small room, things could be more complicated versus in a large one with any sense of that, Evan?
Well, the near field is basically air circulating around the instrument. So that moves with the instrument. So the player's response will probably be relatively independent of the room. People further away will start having kind of an average response across the room.
Well, I mean, if you play in a room, you get the the reflections.
You get the reflections, yeah.
So
yeah.
it sounds much louder in a room than it does in a hall.
Yeah, if you try and play in an anechoic chamber, it's a very bizarre
Mhm.
sensation of the instrument.
Any questions in the chat?
So I have a comment which I think is actually related to one of the points raised by David Morris in the chat. Let's go back to um, the second part of your presentation, and you asked the question, where's the perceptually relevant information? Where does it exist? And so my experience is that the differences between instruments is far less in the steady state, and the majority of the differences in the instrument is in the initial attack, in the transient of the note. So looking at sort of these are effectively long-term averages of the spectral may not be the best way to tease out or figure out the differences. And so that's my hypothesis, is that most of the differences is in the attack of the notes. And obviously the frequency response of the instrument will affect the way that transient and the note attack is, but it affects it in a highly nonlinear, fashion, the way the brain processes it. So that's sort of my hypothesis. And I think it's related to David Morse's comment about, can any of the tests be parsed out to consider the feel of the acceleration of various frequencies, the rise time exhibited, how immediate the perceived sensitivity? I think what he's getting at is he's commenting on the transient of the note as well.
Yeah, I mean, here I didn't look at it because MJ and Sam were always describing the differences I could hear in terms of spectral balance.
Yeah. Mm-hmm.
And so because that's the way they're actually doing it, and I wanted to understand first their way because they did it, but doesn't mean that it's the only information and you're right. And maybe some other people will do it differently or, but it stays in my mind that they are,
It would be interesting to follow up with Sam on this because for decades now, he's been trying to get people, much more interested in analyzing the transients of the starting of the notes. And but I keep on telling him that what?
Sorry, whom?
Sam himself. Yes.
Yeah, but he didn't mention the transient for this at all. That's why.
Oh, I don't know. Maybe he's gotten tired of
No, because we talked. We talked about the transient. So no, I don't think so.
Well, I don't know. I what I tell him is that, well, it's not that we're not interested in it, but that the mathematical tools we have for analyzing transients is very, limited, and because it's by definition, the way the brain processes it is a time varying effect. So we can't, use these linear mathematical tools, like spectral analysis on it. And so all of the tools that have been developed are non-optimal for this.
But hold on, is that right? I mean, let's take a transient of a single impulse. That's what we use to measure the frequency response. They're related, except for playability things, which is Jim's area. I mean, the crunch, the slowness to pick up the Helmholtz resonance. Otherwise, it should be linear. Isn't that right?
No, but here's my point: is that the way the brain processes it is not the way the mathematical tools analyzes it. That's the disconnect. That's why it's so difficult to I think, interpret the results of our mathematical tools, because it's a very poor correlation to the way our brain processes the information.
I mean, the thing is, because I'm using the convolution of the piezo signal, the transient is very well defined in the piezo signal, because it's the time
Absolutely.
it takes to get the sawtooth. And so I could measure this time for different notes, and then look into the convoluted sound files, the same duration, and then see what happens at this level. So that's a...
Yeah, right now you don't have a good picture of a transient to compare with. You know, the spectrum's giving you a picture that people are talking about. So, you know, the processing and visualization of a transient is elusive, to say the best.
Can I feed in a question here?
Sure.
Is there an agreed time varying excitation pattern definition? Is there a psychoacoustically validated time varying version of the patterns you showed? Because that might be the starting point for looking at something that captures transients in elements of them in some agreed way.
The loudness model that I use is a time varying loudness model, but at the end, the only thing I get is kind of the average excitation pattern. So I should have a look at whether I can get the excitation pattern as processed along the time, and see what happens maybe between the excitation patterns at the beginning of the note, between the strata and the degezo, for example. So here it's the average excitation pattern over the whole range of the excerpt. And maybe I could have access, because I'm using a time varying loudness model. So I'm sure I can have access to the excitation patterns that are calculated every, I don't know exactly how much I have, can have a look at this here, indeed. And then I could indeed, instead of comparing the average excitation pattern, I could actually compare to the excitation patterns that I get for different note changes. And
well, or you could have a measure of the difference between two instruments as a function of time. So you could, if you have that information, it still doesn't capture. I mean, Fan is quite right that our brain processes things in a multidimensional way. So the time varying loudness model is still only capturing rather slow elements of transients. It may be that there are things to do with individual nerve firings, which
and the models were designed for, like, were mostly designed to be able to compute a loudness value. And here we don't care about the loudness, and so the time varying is probably a much longer scale for the loudness than it is for detecting subtle changes in timbre.
Okay.
It might be worth asking Brian more that question. He may
but
well
I know
have
that
some software.
At some point when I asked him, I said, you know, with the violins, I get very different answers, even for loudness compared to the loudness model. So if I compute the loudness with this model compared to the loudness as evaluated by players, the correlation is not very high. And I asked him, and I remembered him saying, yeah, it's only a model. The model is based on different sounds. It's definitely not based on violin scales. And, you know, when you judge the loudness on the violin scale, you know, you probably weight in your own mind the lowest register compared to the highest register, and you do all of things. And he said the only way to know is to ask people. No model will tell you, because the models are not there yet. And even for timbre, if you look at the literature, the timbre is always for violins, for instruments of different families. Everybody agrees that the trumpet is brighter than the clarinet. But when you go to the instruments of the same family, then that's where the trouble starts, you know. nobody agrees on which one is the loudest. We were a bit surprised with Joseph about this. There is some agreement in average, but you can have very opposite evaluations by different people.
But we could simply edit out the transients in a recording, and if it is a spectral difference they're hearing, then they still should be able to do it. That would be an easy way to test.
One way could be just to isolate one note.
Sure.
Cut the transient and ask, can you recognize the Strad?
Yeah, but you don't get enough sampling of the whole frequency range. But if you think about it, the Glazunov doesn't have a lot of transients. I mean, it's pretty darn smooth. I mean, by transients, Fan, are you thinking of the Bode transients? I mean, obviously it's full of transients every single millisecond, but
what I mean is that every time you have a bow change or no change, you've injected a transient. Okay. Now the starting of a very distinct bow stroke is, gives the largest difference, but even when you change just the note, even without a bow change, you've injected a transient because it's a new frequency now that you're trying to establish, and then
But
even to a
it's-
lesser extent, but it's noticeable on certain instruments, is vibrato. So as players know that different instruments respond differently to vibrato, and so there's another transient or non time varying signal.
but
So
that
maybe
is
that
captured.
maybe that's a more accurate way is that my experience is that time varying signals on the violin yield a whole lot more information than steady state non-time varying signals.
But I certainly, but you agree that the impulse response captures all of that.
Yes,
I don't think so.
Okay,
Well-
what is missed?
So what's happening in our impulse test, which is what I'd call a ring down test? Nothing's changing in the physical plant.
Mhm.
Okay. So as soon as you start playing with the string and retuning the string a little bit, you're setting up a whole bunch of other interactions that aren't captured in the ring down test. The ring down test is measuring and responding to a static dynamic system, in the sense that nothing is changing in its modal content as we let it do its free decay. It's a very special case. When you start forcing the function, so you're putting energy into the system, you're getting a whole bunch of other artifacts to the sound that's coming out.
Such as?
Such as if you change the string, fret a string, if you will, and put a little bit of vibrato in there, you're changing the modal characterization of the entire instrument to a certain degree. It's small, but you're getting all these modulations that are not happening in that ring down test. The ring down test is about as linear a system as we're ever going to get.
So if I understand you right, we are putting pressure on the instrument, we're damping it in different ways. Is that what you're talking about?
Well, you can do this you can do an analysis of this thing here is take the strings that you have on the instrument and retune them.
Mhm.
Okay. The fact that they're retuned a little bit will change the dynamics of the system.
Oh,
All the
Well,
frequencies.
even by changing an octave, I haven't seen much difference in the admittance.
No, you'll see small changes. We're talking about small changes in transients at this point. You're opening up a whole can of worms here is all I'm really trying to say. Things that happen, in the way this is working fairly well. So I'm not saying this is a criticism here, but in the recorded piezo's, you have the drive point admittance of that instrument. If you take any string and fret it, like go from an open string to play the octave or whatever you want to do there, the modes that were in the system before the string was fretted are slightly different because that one resonator has changed its frequency. Okay.
I'm sorry, what do you mean by fretted? Put your finger down on the fingerboard?
Yeah. play an octave. Guitars, we fret. I don't know what the language is in violins.
Yeah, you put your fingers on
Yeah.
the fingerboard.
Put
You
your
stop
fingers
the
in-
note.
Stop the note at the octave. Now there's a resonator in the system that wasn't there with the open string.
Yeah.
And that,
Oh,
that
sure.
changes things a little bit. So once you get into the physical playing of the instrument, the ring down test is saying we are not changing anything while that whole system decays out and we measure it. That's why that's such a nice clean measurement.
Yeah.
Okay, well, I agree with that. I can't imagine it would be a defining difference between instruments. I mean, there's a lot of things we miss. We damp the strings, and so
Right.
you don't have the same ringiness, but I don't see that we're going to miss anything, but of course I could be way wrong.
Well, what the free body tests do in general, and they're used throughout all sorts of industries and that sort of things. It's a very artificial situation, but it's very repeatable. So it makes a good place for doing comparison testing.
But it's also directly related to the structure.
It's related to the structure in that set of boundary conditions, yes.
Okay.
Yeah.
So as soon as you hold the instrument or mount it to the wall or, in moving equipment around, you get slightly different responses. And when we're starting to look at little details, and you have to dive into all the little details of the measurements, right?
But
We're
the
looking at
thing
some
here-
small differences.
So the thing here is that maybe what happened in real life is, I mean, it's not maybe, it's for sure, is much more complicated because of all the effects that you are talking about. But here, they are not captured and they are not, I mean, so what I mean is that they are not captured because we are doing this convolution with a system that is fixed. But it's the case for both instruments, and they can hear a difference. Is that the difference that they can hear in real life? That's another story. But at least for the purpose of understanding how they do it with these sound files, we don't care about this complication. Now, if we want to translate this to actually what they feel they hear when they listen to the real instrument, that's another step further. But we are not there yet.
Yeah. So
And
this is
within any of our mathematics, we're linearizing them, which is with an inherently nonlinear system. The fact that it works at all is very fortuitous.
Yeah, but here's another aspect of this issue, Joseph. We go back. It's likely. Let's assume that the impulse response or the frequency response, complex frequency response, contains all of the information that we need in the system. Okay, I'll start from there and accept that fact. But the problem is so the issue here then is not whether the information exists. The issue is what is the relevant information. Okay, so the analogy I always like to make is you want to know who scored the goal, in the soccer or football game for Europeans. Okay, and so you see a picture on your TV screen and you can see exactly who scored the goal. Okay, but if I took that cable to your monitor and stuck it into an oscilloscope, that wiggly line on the oscilloscope contains all the information necessary to know who scored the goal. But if you look at the oscilloscope picture, you would have no idea who scored the goal because it's not in the format that corresponds to what your brain needs to know to answer that particular question. Okay, and I think that it's more likely this is the scenario we're in here. It's not that the impulse response or the frequency response doesn't contain the information. The information is there, I believe. Most of the information is there. The question is but what is the relevant part of it? I think this is what Claudia is trying to figure out is, what exactly is MJ and Sam cluing on? Okay, that's enabling them to recognize it.
I agree with that. I would say that, well, first of all, we could never talk about one frequency, one IR. There's an infinite number for each violin. Which one, how many can we get away with? That's other conversation, 12, 1, 2, But on the other hand, the IR convolved with a string signal sounds remarkably like a violin, whereas the video signal
Yeah, I
looks
agree with that.
nothing
Yeah.
like. So we're in the ballpark at least.
Yes.
Okay. Well, anyway, excellent work, Claudia. This is
Yeah. Any final questions? Let's give Claudia a great round of applause, for this great presentation and all the work that you've done over the years. And I know this is work that you've built on over, I think, 2 decades, right?
Yeah, I mean, it's
Yeah, you
continuing.
started a long time ago.
And because it's a tribute to George, I just wanted to finish with a few pictures of him because I miss him greatly and really enjoyed working with him. So it's just for you a few pictures to enjoy collected over the years I've been working with him. Pictures which are related to his biggest skill of like model analysis and tapping and demonstrating it and using his amazing software. All pictures with Knut, who is another person who is greatly missed. That was taken in Jim's garden, doing some. Jim doesn't have an anechoic chamber at his place, but he has a lovely garden, which where you don't have much reverberation. So we did some studies at different. Another nice picture with Joseph that was at Oberlin 2014, so 11 years ago. I know it because I know when my daughter is born, otherwise I would not remember. So these are taken at, so this was measuring the beds. Do you remember this? With people like checking that there was no indent on the violin and George being quite stressed and always checking that there was no indent. We can see some here. This is at our Villefavard workshop. This was an invented picture of George with his sense of humor to show the Bridge Island as being the Italy. What else? So his pinned edge measurement took him a lot of time, and I don't know how many versions he did with, I think with Unai and Roberto. It took about 45 minutes to take the measurement just because you take already half an hour to assemble all the pins. He believes, and this is based on Colin's simulations, that pinning the edge will make the behavior of the plate closer to what you have in a real violin, and that could be more relevant than a free plates mode. But that needs a bit more investigation. Always with this sense of humor, using the pin edge to be funny. Then, yes, that was probably, I think it was my first Oberlin workshop. I entered it in 2010. That was in previous hall, before Kant's hall. Yeah, George was always ready to teach and demonstrate what he was talking about with a lot of people around him trying to understand what he was saying and showing. This is in a workshop we did, a training school we did in Mittenwald. Talking about training school and workshop, he was involved in many of them, and I was happy to share them with him. So we had, of course, the VSA Oberlin workshop, and a big thanks to Fan and Joseph for organizing it over the years. And this Villefavard research workshop that I'm organizing every year. And this was training school that I organized with George for a few years. And then COVID hit, and then we never had the courage to restart it because it was a lot of work to have it travel across Europe. So we finally did only the Villefavard workshop. And then, yes, so I can't recall the endless discussion between George and Colin, always arguing. Very high respect between the two, and always arguing and interestingly arguing. Yeah, I have to thank Jim as well for welcoming us for many different little workshops at his place. Very high hospitality and generosity. So that was quite a long time ago because there was Knut and Anders and even Joseph with long hair. So that's been a long time ago.
Is that Charles Besnay new there?
And Charles Besnay,
Yes.
yes, and Thierry. And yeah. And yes, model analysis with Unai, who is probably the biggest tapper in the world, especially after the Bilbao project. Yeah, so that was one of the first workshop in. That's where we see that we have all aged quite a lot.
Nah.
That was, yeah, probably
Not me.
2008. Yeah, you never had hair, so it doesn't change.
Oh, ouch, ouch.
And what else? So yeah, so Bilbao project, that was a big thing. A lot of work for a couple of years, and then a lot of fun at the end to celebrate the end of the project with funny pictures. We went partying all night. Yes, with yeah, basically many listening tests that I did over the years, and where many of them George was involved, especially in the different training schools that we did in Ghent and Mittenwald. Yeah, it was very active in the Wildflower workshop, always giving advice to the makers who were around to tell them what he thought about their instruments after the listening test, and very generous about his time and his knowledge. Other pictures. So this is it, Oberlin. This is in Wildflower. Yes, and to finish, some fun pictures. Maybe this one I should not show it, but fun picture, like celebrating the end of the Bilbao project and drinking a bit too much probably. And that's it, yeah. And that was back. We were coming back from the US, and we got both of us got. Stopped in New York. No, not in New York, somewhere, I can't remember. No, in Cleveland, because of storms. And so we ended up being stuck at the airport and had to find a hotel. And so we found a motel, and for me, it was my first experience as a. Before I knew the US, basically based in from New York, and my visit in Hawaii, and then Oberlin. And I think it's very non-typical of the rest of the US. And so that was our experience, going to a motel with neons flashing, and then and it was quite funny to share the room with him in this completely random place. The US as I imagined it from a European perspective, and that was quite funny compared to what I had seen in the past. And I think that's it. Yeah.